Your CPU is overheating, but the real question is the problem the chip or the heatsink? Not all heatsinks are created equal. Material choice and how a heatsink is made can make or break thermal performance. Today we'll break down how heatsinks are actually made. Before we get into specific methods, let's clear up what a heatsink actually does and why the heatsink's manufacturing process matters. A heatsink isn't just a slab of metal with some fins glued on. It's a thermal system. Its job is simple sounding. Move heat away from the hotspot, the CPU, GPU, or power transistor, and dump it into the air or coolant faster than the component can generate it. But the way it moves heat actually works three ways. Conduction. Heat travels inside the metal, from the chip into the base, and up into the fins. Good internal conduction means the heat reaches the fins quickly. Convection. Once heat is on the fin surface, it transfers to the surrounding air, or liquid. This depends on fin area, airflow speed, fin spacing, and surface roughness. Radiation. Small but real. The fin emits thermal radiation, usually minor compared to conduction-convection, but it can matter in vacuum or high-temp situations. Besides how it moves heat, the way a heatsink is made is just as important. The manufacturing method determines fin thickness, spacing, how well the base contacts the component, and even microscopic contact resistance. Two heatsinks can look nearly identical, yet one performs much better simply because its fins were skived from a single block, zero interface resistance, while the other had soldered fins with a thin void or oxide layer. So when you judge a heatsink, don't just look at the number of fins, ask how those fins were made and joined. Now that you know what the heatsink needs to do, there's another key factor we need to consider: the material itself. Different materials can dramatically affect a heatsink's thermal performance. Material choice is always a trade-off. Copper. Thermal conductivity, roughly 308 to 420 watts per meter Kelvin. It's a superstar for thermal transfer, so you'll see it in high-end AI servers, GPUs, RF amplifiers, and anywhere every fraction of a degree matters. Aluminum alloys. Conductivity roughly 150-250 watts per meter Kelvin. Lighter, cheaper, and very easy to extrude or cast. That's why it's common in consumer PCs, automotive electronics, and outdoor power modules. Advanced composites emerging. Graphene-reinforced aluminum, diamond metal composites, etc. In lab settings, you can see numbers like 350 watts per meter Kelvin, or even 500 to 600 watts per meter Kelvin for diamond aluminum, and theoretically up to 1,000 watts per meter Kelvin for diamond copper mixes. Amazing on paper, but hugely expensive and difficult to mass produce. Quick line. In theory, diamond is the ultimate heatsink material. In reality, your purchasing manager usually says no. Now let's dive into the most common manufacturing processes and why you'd choose each one. 1. Aluminum extrusion. Think Play-Doh for engineers. We push softened aluminum through a die to make long profiles with integrated fins, then cut to length. Pros: very cost-effective for medium and large volumes, good mechanical strength, consistent cross-sections. Cons: limited to 2D profile shapes, long straight fins, surface finish, and thinness limits. When to use: mainstream PC coolers, power supply heatsinks, and LED housings. 2. Die casting. Melt metal and force it into a complex mold. Great for 3D shapes and integrated housings, fan shrouds, heat spreaders with mounts. Pros: complex geometry, decent cost at volume. Cons: porosity can hurt thermal conductivity. Typically, coarser grain structure than forged or extruded parts. Best for shapes where complexity matters more than top-tier thermal performance. 3. MIM. Metal injection molding. Like industrial 3D printing's cousin, metal powder mixed with binder is injected, then the binder is removed and the part is sintered. Pros: enables complex geometries and fine features in high melting point alloys, including copper-based. Cons: sintering shrinkage. Cost per part can be high for small runs, and material purity matters for thermal paths. Use where complex topology equals better cooling or compact multi-directional fins are needed. 4. Stamping. The cookie cutter approach. Punch fins or plates from sheet metal using progressive dies. Fast and cheap. Pros: extremely fast, low cost per part in high volumes. Cons: usually limited to thin fins, used for low power or compact devices, typically under 5 watts per component. Common in small electronics or inexpensive laptop sheets. 5. Forging. Smash heated metal into shape under huge pressure. The result: dense, refined grain structure and great conduction. Pros: excellent thermal path, mechanically robust. Cons: expensive tooling and presses, used for premium parts where performance justifies cost. 6. CNC machining. Multi-axis machining shapes complex curves, pockets, and channels with extreme precision. Pros: ideal for prototypes and small batches, precise features for high-frequency RF or 5G amplifier heatsinks. Cons: slow and material waste heavy for large volumes. Use for prototypes, custom small runs, or super high-precision parts. 7. Skiving. The butter slicer. A blade slices thin fins directly from a solid block. The fins remain integrally bonded to the base. Pros: zero interface resistance between fin and base, allows very thin and dense fins. Excellent performance. Cons: tooling complexity and limited to certain geometries. Best for high-performance CPU, GPU air coolers. 8. Zipper or folded fins. Stamp thin sheets, then fold or lock them together like metal origami. Pros: super thin fin thickness, very high fin density possible, used in high-end air coolers and compact radiators. Cons: mechanical joints must be precise to avoid extra thermal resistance. 9. Swaging. We machine grooves into a base, then press in fins with massive force so they press fit at near atomic contact. Pros: no solder or adhesive, extremely good thermal contact. Cons: heavy presses and tight tolerances. 10. Reflow soldering. We attach dissimilar metals, e.g. a copper base to aluminum fins, using solder paste and a reflow oven to form a permanent bond. Pros: combines the best of two materials, conductive copper base plus light aluminum fins. Cons: requires careful process control. Poor reflow or contamination can create voids and raise thermal contact resistance. Once the heatsink is formed, the surface finish becomes another key factor. It affects durability, appearance, and in some cases, thermal performance. Now, let's dive into the different types of heatsink finishes. Anodizing, common for aluminum, provides corrosion resistance, electrical insulation, and that sleek black or silver finish. Electroplating, nickel, silver, often used on copper to stop oxidation, that green patina, and for a premium look. Epoxy powder coating or paint, used for environmental protection, outdoor electronics, but thick coatings can add thermal resistance if you coat mating surfaces. Now that you understand how materials, manufacturing processes, and surface finishes affect a heatsink's thermal performance, it's easy to see just how much engineering goes into keeping our devices cool and stable. If you need a reliable manufacturing partner for your heatsink project, RapidDirect provides one-stop manufacturing solutions tailored to your budget and performance needs. If you found this video helpful, don't forget to like, comment, and subscribe. We'll keep bringing you deeper insights into manufacturing, materials science, and real-world engineering.